Welcome back to the OnTrack Podcast. I'm delighted to have back in studio Ben Jordan, my friend and colleague. We always enjoy talking about manufacturing and design and all the implications. Today we're going to talk about reliability, and we're also going to talk about the hazard of data sheets. When are they accurate? Can we rely upon them? And some things that come up. And he takes a question off the forum that talks about gilding. You're going to enjoy this one and hopefully have a few laughs. We'll see you on the other side. Welcome to Altium's OnTrack Podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Wait a minute. Before we get started, we've got some exciting news. Altium has some amazing limited time spring specials that we just have to let you know about. Right now, you can save up to 45% when you upgrade to Altium Designer 19 or add additional licenses. The offer expires May 22nd, 2019, so don't wait. Check out the Altium website at altium.com today to learn more. And now, let's jump right into another great conversation on the OnTrack Podcast. Welcome back to the OnTrack Podcast. Today, again, I have the pleasure of having my friend and colleague, Ben Jordan. We always have great conversations around the office, and
we do.
It's super fun just to do this in front of a camera so you can witness the little rabbit holes we go down.
Oh, it's fun and a little bit dangerous. But hopefully not today.
Yeah. So we promised that we would do sort of an Ask Me Anything, and again, you can always email us on ontrack@altium.com, right? ontrack@altium.com to ask us questions specifically. But today we're going to be pulling something funny and odd that we saw on the forum that just took us down one of those rabbit holes.
That's right.
So, Ben, why don't you share what you found on the forum?
Sure.
And then
I like to catch up with our lounge forum pretty often, at least every week or so, because there's always something very amusing going on in there. And often there's deep technical things going on too, which are fascinating to me as an engineer. But this week, one of our users, Tim Phillips, posted a really odd data sheet that he'd come across for an inductor. It's called a common mode choke, right? Mm-hmm. These are parts that go into power supplies for reducing conducted emissions out of the device, and also clean up some of the common mode noise going into the device. But that's not the point. But in his forum thread, he started the post by saying, "I ran into an unusual data sheet from Murata for a Murata common mode choke, and on page 7 it says, 'Do not use a gilded pattern. The copper wire may cause open by dissolution of metallization.'"
Say what?
And even though it's written in English and it's using correct language,
right?
Technically correct language. So this is a good example of how crazy data sheets can be sometimes. To me, what that says is the first language that the data sheet was written in was not English, and they translated it. So
where's Murata from? Japan?
I believe Japan initially, but they're as far as I know, a global company, just in the same sense that Altium is global. They have offices and
many countries,
subsidiaries all around the place, right? Mm-hmm. Doing different kinds of things. Some of them make inductors, some make capacitors, and they're probably in different locations. But Gilded, and then this whole forum thread ensues. What does Gilded mean?
What I love is what the guy said below him. Read that.
Let me bring that up real quick. So there's a few interesting threads here, but
the one, the never have I ever. He was basically asking, has anyone ever seen this
Yeah.
note and what?
Brad Verlander chimes in, well, I've never seen such a note in all my life.
I'm right, Gilded.
And then Darren Moore comes in, looks like they don't like hard gold, and introduces another interesting word, embitterment. And
Which
then
I thought I was smarter than Brad, and I thought he meant embrittlement, to which Ben Jordan said...
Well, embitterment is absorption of atoms in between the crystal lattice of the metal.
Had no idea.
And then that creates embrittlement as a result of it.
See, so embitterment is related to embrittlement.
But I had to go look that up. I didn't know that before I read this thread.
Oh, you didn't?
That was something
Oh, well,
Darren
you
Moore
like
introduced.
totally... I thought...
I'm like, what are these guys talking about? I've got to go. I feel stupid now. I've got to go Googling all this information. But I just...
See, you shouldn't have told me, because
hilarious.
I thought you actually knew what embitterment and embrittlement... Like, I didn't know you'd already Googled it.
By the time I spoke to you. So that's my secret. Don't tell anyone.
Okay.
I consult the oracle, known as Google, on
Yeah,
a lot
right?
of things.
I know.
But it's just, I can't help but wonder if the person who wrote the original data sheet at Murata, who maybe it was the engineer who developed that series of common mode choke parts, which are pretty common, well understood parts, right?
Mm-hmm.
If that magnetics engineer could see us now and see our forum and understand the kerfuffle that using different words has caused.
Well, until you told me, I wouldn't have thought about that it was written in another language and then translated, thus resulting in the word gilded.
It may, I mean, there's a chance it was written in English and they just chose esoteric words.
If it was, that person should not write any more technical data sheets.
Probably not, you know. What's the rule for, the golden rule for writing, for business writing, is target what age group?
Golden rule? No pun
Golden
intended,
rule?
right? This is what we do.
Yeah.
And then we went down the whole gilded. Then we started, the only thing that I remember the word, well, there's two references to gilded I remember. This is a little off topic, but gilding the lily. So we actually went on Google and looked that up about, that's sort of over embellishing something that's already beautiful.
Yep.
And what was the other one about the bird in the gilded cage or something? You mentioned a Rush song.
Yeah, so there's a Rush song called Limelight where there's a line about how being a famous musician is like living life inside a gilded cage. From the outside, it's all amazing and gold and shiny, but you're still in a cage.
So Ben and I, so he showed this to me. We had a good laugh and then started going down, like I said, this rabbit hole together. And then I remembered Rick Hartley, who, for those in you in North America, you're probably familiar with Rick's speaking at PCB West and DesignCon, different places. But he always starts out his talk when he's talking about field theory particularly. He always has this quote, and that made me laugh that first time I heard it. And he said, "IC app notes should be assumed wrong unless proven right."
Guilty until proven innocent.
Yes. That was a quote by Ricci, and he said he's been using that quote for 25 years.
Yeah, I've read it in his books.
Really?
Yeah, read the same thing.
So then, again, continuing down this path, so I emailed both he and Dan Beaker. Dan Beaker works for NXP Semiconductors.
Mm-hmm.
He's talked about IC app notes, and then so I sort of asked them, Ben and I want to talk about data sheets and app notes. What say you? And they brought up a couple few things that I think should we finish discussing where we went with this note and what we decided it really meant?
We did come to a conclusion, and you can look this up on the forum too, but we'll come back to that at the end of the podcast.
All right.
But there was some clarification obtained in the long run, but it took a bit of back and forth.
It sure did.
So but this whole app note and can you trust them is actually a really important question, and some of you may know my background in engineering is more on the computer systems side. I studied hardware design, but also programming and software, and I came to Altium originally as an FPGA designer, and I got my PCB chops, you might say, while working at Altium over 14 and a half years. So in the first year I was working with this company, I got to design a prototype board for a video A to D converter. So it would allow you to plug a composite video signal in, and it would convert it to a USB. I think the board had USB and video input on it actually. But the analog to digital converter for sampling a video stream and turning it into digital format that could be processed inside an FPGA.
By the way, pause 1 second. For those of you that are young designers, you may not recall, we do not make hardware now, but there was a time where Altium made FPGA boards, right?
Yeah, we had a product called the Nano board. We had a whole team of hardware designers, at first in Hobart, Tasmania, then in Sydney, and then in Shanghai, China. And then that sort of product line was retired.
And a lot of ProTel or people that have been with Altium Designer as a tool for a long time will remember that, but some of the young ones might be going, wait, what? You guys design hardware? We did.
And that might be one reason I could say that we have a user-friendly UI. I mean, that's subjective and anyone can argue over that. But honestly, we had a bunch of internal feedback from real designers going on daily.
Right.
With R&D. I remember when I was back in Sydney in 2009, 2010 and so on, we had the hardware team sitting right there as part of R&D along with all the software developers in the same room. So
what a dynamic.
If they encountered some real irritating bug, they would go and talk to the guy and say, let me show you this thing. You go here, click there, do that. Now you see you get this crash or whatever. So that was an interesting time, and I think a lot of good things fell out of that. And some of our hardware developers ended up forming what became the content team that developed all the library components that our customers enjoy. And so some of those people are still around in different parts of the world, contributing to all the symbols and footprints that you can get on Octopart, for example.
Interesting.
But in that process, I got a chance to design a board for a prototype for a video peripheral for this Nano board, FPGA board. And I read the app note and followed the app note, which said you separate analog ground, the video ground, and the digital ground. And this app note, this is something that Dan and Rick and others talk about a lot in app notes. They frequently say separate your analog ground and your digital ground because they're concerned that there's noise, electrical noise in the ground from the digital circuitry, and you don't want any of that going anywhere near your analog inputs to make your input noisy. But the prevailing wisdom now is you just have one ground and you don't split it up. And I got this hard firsthand because here was I coming in wet behind the ears, having only ever done hobby PCBs up until that point, really. And I just followed the application note and separated my grounds. And then the experienced professional PCB designers on the team, that was their first criticism of my design and shot.
Oh, so it
functioned okay, but they shot it down in flames as being a poor design because they're like, why did you separate the grounds? It's complicated, and the application notes are usually wrong.
To Ricci and Rick Hartley's point, right?
Yeah.
But let's talk about why that happened. So Rick had said to me, I actually talked to Rick Hartley on the phone last night, and he goes, IC or app notes and data sheets are both produced by IC engineers, not board engineers, and usually not people who understand field theory.
Right. It makes sense.
And it makes sense why sometimes you have trouble with your data sheets.
Yeah, because they're, and I've heard some. This is probably not always the case, but I've heard some people make statements like the data sheet is really just the marketing vignette for the part.
Yeah.
Maybe, it's got to contain factual data because people will legally hold the manufacturer responsible for what's printed in that.
Right.
If you design that into something and it doesn't work as advertised on the data sheet, then in theory you could, hold them to task over that.
But that's a little like, I'm just putting myself in a designer's shoes. So you're working from unreliable data sheets. So Ben Jordan, how do you work around there? What's the solution? And then you're getting people having words like gilded on their data sheets, and it's like, what are you talking about?
Yeah.
And gilded with what? By the way, let's just talk about gilding. So we're guessing they're talking about gold, but it could be silver.
It could be.
But is gilding only relative to gold? We'll have to Google that one later.
Yeah. So that's a good point and a good question. So when I've designed with a number of different chips and digital land, analog land, mixed signal land, and what I've found is almost always the data sheet may contain everything you need, but you need more information. So you turn to app notes, or you will download reference designs. This is a pretty typical thing to do. And everybody is so under the gun to get things designed these days.
Right.
You almost have no choice but to take it on face value that if you download the schematics of the development board from the manufacturer.
Yeah, but that's a simple board.
They can be, or they can be really complex. So let's say I was designing an audio signal processing product, and I'm using some sort of digital signal processor, and so I have a development kit from the manufacturer. There's tons of these out there, but they're actually, I had one DSP development kit that had something like 16 analog inputs and outputs on it, way overkill, and the end product I'm going to design only needs 2 inputs and 2 outputs.
Oh.
So, for stereo audio.
Right.
2 in, 2 out. And where do you draw the line? They're going to have, for a product like a processor or a digital signal processor, they're going to cover a lot of bases or use cases in the application, in the development board or the eval board, whatever you're using. So you've got that as a starting point for your own hardware design, your own PCB design. You can start with that. But sometimes figuring out what are the bits that are actually needed, that we're actually using, and what aren't you.
Because they're preparing for every eventuality.
Yeah, they're covering in true engineering style, every corner.
Right.
Every corner. But most end products don't cover every corner, don't need to.
Right.
So that's the question, where do you draw the line and decide, how do you figure out what you need and what you don't?
Yeah.
And it really depends on the quality of the application note and the reference design that you're working with. Unfortunately, it's like how long is a piece of string, to me anyway. In the case of that video A to D converter I was talking about before, that request of the test engineers and the application note to separate analog ground and digital ground was completely unnecessary. They go overboard, And that's, I think that's
Right,
something
I think,
else.
right. So when Rick and Dan emailed me back, they both talked about that they are conservative in nature.
Mm-hmm.
Again, to your point, maybe because of legal implications or accounting for every eventuality or whatever. But that really doesn't get you to necessarily what you want to do.
Right.
Right? So how do you get to a point where you personalize it?
Well,
or,
that's where I think being an engineer, being a designer, that's where your training comes in, really, because anyone can take something off the shelf that's already there and it already works, and all you have to do is program it differently. If you're going to do that, you can. There's a lot of good prototyping platforms out there, like Arduinos,
right,
of various shapes and sizes,
right,
or Raspberry Pi. Raspberry Pi actually not, because it's not open source, so they don't give you the PCB design to start with. But those are. It's more like those are computing platforms which you reprogram to, like, your secret source is all in the software.
Right.
For most of us, there's a bit of both. We need custom hardware and we need custom software. And starting with these reference designs is a good place to get things working. But you need to.
That's the starting point.
That's the starting point. You need to apply your engineering knowledge. And it's the same with datasheets. They'll make all these claims as to operating values, voltages, currents, temperature ranges, and again, to your point and to Dan's point, they're always very conservative. I've made plenty of little devices and gadgets that used parts outside of their normal operating conditions, way outside, and they function just fine. Right. If you know what you're doing, you can push things and you can use them in weird and wonderful ways. I'm not advocating people do that, but
I'm thinking, but you're like making some pimped out amplifier so you can play guitar with it. It's not a jet.
Exactly. If it blows up, it's going to disappoint me, but it might actually be fun pyrotechnics.
It won't kill anyone.
So that's a good point. There's different markets here. There's things where somebody's life could be on the line. Medical, aerospace, automotive. Automotive is a really important one. And I think when you read a data sheet and you look at those extreme values, ratings, and all of that stuff, the safe operating area of devices, that's what they're targeting. They're targeting that worst case scenario where the environment's very harsh, or it's going into space and the temperature extremes are the greatest. And those are there to tell you, this is what we guarantee it will work to. We guarantee these values. And you must check the errata, because sometimes they make a mistake and have to update the document.
I don't know. I come from a fabrication side, so when I always imagine you engineering people, this being such a fixed, hard science, data, so it just is bizarre to me to think about data sheets. They're put together like engineers, covering all the bases, but it's like, I don't know, I just assumed really the data sheets would be kind of flawless, like
they're close. They're. I think in our industry they're as close to flawless as you could hope for, but they're still errata, And
so
they're still ultra conservative. So you need to talk to your applications engineers who know those products, and who are often the ones who did the testing for the semiconductor in the semiconductor lab. They're the ones who did the testing to write down those values and compile the data for the data sheet. Talk to them. Get somebody's email address, verify things. Find out, hey, I know the data sheet says the temperature range is minus 25 to plus 40, but could I reliably use this part to minus 85? And they'll probably say, yeah, absolutely.
Right.
Right. They may not. They might say, well, you have to buy the extended temperature variant, which costs a little bit more, but that's when you're actually paying for some warranty at that point. That's what you're getting. I see. And the other side of all of this conservative data sheet sort of notion is you have to measure it. Like there's no substitute for actually.
Yeah.
You get a bunch of them and measure them yourself.
Yep.
You can't always do that. Not every part. Sort of some complex parts like microprocessors won't lend themselves to that. But there's a lot of things you can do, and really there's no shortcuts. There's no real shortcuts to actual measurement. You've got to have a lab and you've got to do stuff in the lab to have your own confidence that what you've designed is going to work.
I'm going to read this. So this was an email I got from Dan Beaker from NXP this morning, and his concluding sentence said, device specifications are conservative by nature, which we said. The supplier must cover all aspects of possible use to protect themselves from liability. We said that.
Cover all the corners.
And again, it's important to compare these specifications to your requirements, and for critical elements, even do your own testing.
Do your own testing.
You pretty much just summed up, what Dan Beaker is saying.
It's almost like I read that email already.
Right.
No, but I would have said the same things. I mean, it's true. And Dan, and don't take it from me, take it from Dan is a known expert in this field and is constantly calling out flaws. It's part of his actual day-to-day job is to correct data sheets and app notes for NXP. That's part of what he does.
Right. I wanted you to comment on this too, Ben, what you thought. He also said data sheets and app note schematic examples are notoriously conservative. We said that. Mm-hmm. While they may be functional, they'll probably result in higher BOM costs.
Yeah, and that goes back to being able to what I was mentioning before. My way of sort of long-winded way of saying the same thing is you start with a reference design or an eval board, and it's covering every possible use case of the part. So you can test and evaluate it for yourself, right? So test, evaluate. But at some point, you're going to take the schematics and maybe the PCB as well for that eval board or prototyping kit or whatever from the semiconductor company and modify it to become your own product or your own module. And where do you cut things out? And this can go to the extreme of, and many people who've done offshore manufacturing know that this goes on. There are optimization teams at some contract manufacturers that do assembly for you. You give them a test criteria and they do bare board and in-circuit testing. And before they go to full-scale production with all the pick and place and automation, they'll take your prototype and start removing capacitors.
You told me this a while back and I could not believe it.
One by one until it fails, and they put the last one back on. And this is going to be happening a lot right now because parts like that are on allocation.
Precious, right?
Yeah, I mean, who knew the second most common part after the resistor was going to be a hot commodity like that?
Like we'd run out of pennies, right? It's crazy. But I remember you telling me about them plucking those off until it failed and then putting the last one on. But
an example of what Dan is talking about is I've looked at a lot of audio circuits just because I'm a musician and I'm into audio electronics, right? So that's what I do on nights and weekends when I have a spare moment. And I see a lot of reference designs where they're using really fine values of resistors everywhere. They'll have a power amplifier circuit and an engineer has calculated the exact resistance values needed to the second decimal place.
Right.
And then they'll go to the most granular resistor range. It's E192, or there's even one more granular than that, I believe. It's like an ISO standard resistor value range, where they're all within 0.5%.
Oh, wow.
It's crazy.
Yeah.
And so they have all these almost exact resistance values everywhere, and it's, for most of the time, it's totally
Overkill.
unnecessary.
Yeah.
It's totally overkill, and those parts become hard to get and expensive, and that's what he's talking about. That's just one example. Another is, again, going back to the DSP development boards I've used in the past. They had a lot of additional memory, for example. They had extra dynamic RAM chips on them. Way overkill for what I needed. Like, I could record 10 seconds of audio at a normal sample rate in those, and it's way overkill. I only need, a second and a half of buffer size for audio samples. So there may be 3 times the amount of RAM chips on the reference design than what I actually need for my application. That's an obvious example, but it goes from that kind of level all the way down to the capacitors, where in a contract manufacturer scenario, they may be taking them off the board until it fails and then putting the last one back on and saying, that's what we're going to make, just to save money. That's
crazy. I mean, again,
and it's like, you've seen it in PCB manufacturing. It's the same. People way overspec their boards.
They do. They overspec materials and overspec, and we're always talking about...
It's got to be exactly this thickness dielectric, and you're like, we can get what you need using our processes, and we don't... It's going to be within 1% or 5%, and that will work just fine. You're like...
Or they may need heavier copper or heavier something in one area, but that just like do it to the whole board. Well,
yeah, it's like, why?
Why?
And then
because you can do it selectively.
Yeah. And then, or Rick, I remember telling me an example of, he went in, a project kept getting stalled, and they had 8 layers of copper.
Yeah.
No, it was 18. It was 18 layers. And they thought, the designers thought they needed all these plain layers for power and ground and shielding and all sorts of... And they were just way over conservative. And he reduced it down to 4. 2 signal, 2 plain, worked beautifully, routed easily.
Speaking of which, I'm going to share this talk in the show notes, because Rick Hartley, that was in his Stackup talk, was it not, at Altium Live? At least
it may have
part
been.
of that. He talked about it.
He's mentioned that one a few times. Yeah.
So I will make sure, I'm going to share talks both from Dan, who talks about all about the space, and Rick Hartley, who talked about Stackups that are nutty, and why they're nutty, and again,
Well, length tuning is an example of that.
Right.
Like, people think they have to tune memory lanes to within 1 mil. Well, how many picoseconds is 1 mil on a PCB?
Exactly.
It's a fraction of a picosecond.
Right.
Your memory bus and timing is never going to need that.
Yeah.
Like, well, not in current technology. You've got way more room to breathe in
a little
with
bit,
routing,
right?
And you don't need to be. And you can slow, with some of these products, you can slow down the clocks and slow things down so that you don't need to go to that degree of length tuning. That's a good example, because if you have to tune a bunch of traces to that level of accuracy, it's going to take up a lot more space on the board.
Right.
Tons more space, and then you'll need more layers.
Yeah. I think, too, when we design on these screens where everything's like blown up so big, that we really forget what 1 mil looks like in real life.
Yeah.
Right? I think our hair like 2 mils or something? I don't know. It's a ridiculous...
My hair is 0. I have 0 mil hair. You can see it.
You have perfectly tuned hair.
It's length. My hair is length tuned to 0.
Oh, you are funny.
I'm allowed to say that.
You are funny, yeah. You can say it. I won't say it about you. Oh, my gosh.
So
Yeah. So I think, so thank you. That actually helps me relate more when you talk about the board fabrication or CM side where things are overspecified.
yeah,
That helps me understand it
and
because I think of engineers being so uber precise and,
right.
you know.
Yeah, this reminds me of a joke that my father keeps telling me. He's an accountant. And the first thing he says is, because I'm an engineer, he's an accountant, that we're mortal enemies. So I love you, son, but you're a mortal enemy.
Wait, don't both
Engineers and accountants are always at odds.
Why? They're both
says,
math.
You engineers, you want everything in bloody stainless steel. But it's funny because it's true. Engineers, we want things to be perfect. We love excellence.
Right.
Engineers value excellence. That's why a lot of engineers are into music and things like that, because it's a mathematical thing that's in the mind.
So mathematical.
But it requires a sort of certain precision, and engineers value precise things. We see beauty in that.
But your data sheets and app notes are out of control, and you just don't want to gild things. That's what I'm saying. The irony.
Maybe that's why they chose the word gilded.
But that's what gets me is I experience engineers as excellent, and I think of precision. So when I think of the irony of data sheets and app notes, I'm like, wait, what? But now you know what's happened is you've precisioned yourself into a corner with
exactly
the every eventuality and the liability. So let's just kill it.
It happens,
you know?
but it happens all the way through the value chain. People will overspec parts. They'll say, engineers are often pragmatic too. So if it comes to something like temperature range, they'll say, well, where is this product going to be used? Is it under the hood of a car, or is it a consumer device in somebody's pocket?
Mm-hmm.
But often we way overspec things. We say we want all the resistors to be 0.5% tolerance. Most of the time that's totally unnecessary.
Right.
We just end up with a bloated, expensive product if we go too far with that.
Right.
So
the overspecking when you're doing prototypes is tolerable. If you take this into production, it'll kill you.
Mm-hmm.
It'll kill you.
Yeah, I see it a lot with devices like FPGAs, and their decoupling is a good example. People have no real good idea what kind of decoupling capacitance is going to be needed for an FPGA, because you can't predict how much energy and what kind of signal switching and all of that. It's a complex system.
Right.
And honestly, the best approach to that is you go overly conservative for your prototype. Then when you get your final firmware running in it, then you test it and you take things away until you have enough, but not too much.
Right.
And plus some margin for safety. And you do all your testing with that, and then you go to production. But again, it's like you can't avoid getting into a lab and doing testing and experimentation.
Right.
You've got to do it, or you'll end up with a product that's no one can afford.
Yeah, data by definition is measured, is it not?
It is.
So there you go.
Measure it, and we love test equipment. We're all about the test equipment, us engineers. So it's a good reason to go out and get a new oscilloscope, I think, a logic analyzer.
Eric Bogatin would like that with his Teledyne LaCroix tools.
Yep.
Oh, I'll share that one too, because that's a measurement, right? And Ultima Live, he also taught how to use an oscilloscope properly.
Oh, that's great.
I know. I never actually had the opportunity to watch that. So
and some of us
I'll
need
share
a
with
refresher.
You guys. Yeah.
Because the technology grows and changes.
does.
So to come back to Gilded, there was a follow-on thread, and actually in the end, they emailed the excuse me.
The original
They
guy?
emailed the Murata technical support,
okay.
and they came back saying yes, Gilded means gold plating.
Okay.
So if you have hard gold or immersion gold with that part, they don't recommend it because of the diffusion of gold into the copper, and it can disintegrate and the part can actually fall off because it's a heavy part. Now, I've actually seen that. I remember doing an IPC training years ago, and the teacher brought in a board with a bunch of D-packs that were soldered over hard gold, and he said, just grab one of those D-packs with your fingers and pull it off. They were soldered onto the board, and we could literally just grab them and
pull them off. They
would come off because the hard gold plating and the solder don't play well together. So there's metallurgy, this is the material science of PCB assembly, and maybe that's another topic for another day that we
another topic another time.
Get into, yeah.
Because they're all that like surface finishes.
There's so
and
much.
What metals play well together.
Yeah, and where should you use them, and with what other components, and what are the limitations?
And it's a never-ending web. If this, then that. If this, then this. Right?
Yeah.
That's a tricky one. So, well, Ben, this has been fun.
Has it?
Well,
I had fun.
I had fun. I had fun. I hope you had fun.
I did.
Going down the gilded rabbit hole.
The gilded hole. Gold-plated vias. That's what that means. The gilded hole.
Yep, that's it. So this is the kind of bizarre things that Ben Jordan and I talk about when we're not busily doing our jobs here at Altium. So as I said, I'll share some things relative to the things that Ben and I have talked about. I'll certainly share. Thank you, Rick Hartley, and thank you so much, Dan Beaker, for emailing us and filling us in and helping us, kind of understand these crazy issues. And I hope for our listeners this has been helpful. Why data sheets and app notes are the way they are, and I hope you had some fun along the way. So thanks for joining us today. We look forward to hanging out with you next time when Ben and I find some other goofy thing to talk about.
Yep.
So thanks for joining. Are you going to go out with me again? So we'll see you next time. Until then, always stay on track. You blew it. Okay.